Right. Happy Thursday. Looked at infinite series last time. What is an infinite series? How do we sum an infinite series? We also looked at the divergence test, right? And what a geometric series is and when it converges. And what it converges to. We now study series with positive terms. So where every term of the series is positive. We're also going to be introducing several new tests. So let's just jump right in. Want to examine this series for convergence. Again, let's put it in sigma notation.
Let's start at 1 and do 1 over the square root of when left.
That works. No, it's not geometric. Limit 0. The divergence test fails. I'm gonna use the integral test. So replace a sub n with f of x. Where f of x is continuous, positive, and decreasing. On the interval 1 to infinity. If the integral from 1 to infinity of f of x converges, and so does the series. If the integral diverges, then so does the series. And so really we can write this as an if and only if statement. When its series converges, if and only if the integral converges. So we set f of x to be 1 over the square root of 2x minus 1. Clearly, it's going to be positive. And it's continuous. Should also be clear that this is decreasing. It's not clear, take its derivative. -1 over the quantity 2x minus 1 to the 3/2. There are no points of discontinuity on our interval. Right, this means that f prime is defined everywhere. It's also clearly never equal to 0. So we have no critical points. So the derivative is less than 0 for all x in our interval. Hence, f is decreasing. The conditions of the integral test are satisfied. So we want to take that integral. If that converges, so does our series. If that diverges, so does our series. Right? Limit b approaches infinity, integral 1 to b. Antiderivative 1 over root 2x minus 1. That's going to be a u sub. Multiply by 1/2. And that's 2 times u, 2 times root u, which is just 2 times root 2x minus 1. Evaluate this from 1 to b. What is that limit? That limit is infinite. So the series diverges by the integral test. Sum n equals 1 to infinity of 1 over n cubed plus 2. Not geometric. Divergence test fails. Suppose we could use the integral test. No, we're not going to be able to. 1 over x cubed plus 2 has no analytic antiderivative. So integral test isn't going to work here either. One of two comparison tests, the direct comparison. Let 0 be less than or equal to a sub n, less than or equal to b sub n for all n greater than or equal to 1. If the series b sub n converges, so does the series a sub n. If the series a sub n diverges, then so does the series b sub n.
On that, can you flip flop the order strictly vice versa? Like if a sub n converges, does that mean that b converges?
No, so it is strictly just this. Right, and the idea is this, right? So if you take a smaller value that converges, does that mean the larger value has to be convergent? No, right? Infinity's larger, but it diverges. One of the most common errors I see with this test is students will find a larger series b sub n that diverges and conclude that the original series has to diverge, which again is not true. Right? You find a larger divergent value, but does not mean that the smaller one diverges. So the key to this test is you have to look at it and decide, does it converge or not? Do you think it converges? If you do, then you want to find a larger value that you know converges. If it doesn't, you want a smaller series that you know diverges. I'm going to introduce a new series. Called P series. P series is any series of the form 1 over n to the p and goes from 1 to infinity. Converges only for p greater than 1. It diverges otherwise. Summation n equals 1 to infinity of 1 over n is called the harmonic series. The harmonic series clearly diverges. It's a p series with p equal to 1. Right? So we've determined we want to use direct comparison. We now have to decide, do we think it converges or diverges? Because that's going to dictate if we have to find a larger value or a smaller value. So that means we have to find a larger value. Well, n cubed plus 2 greater than or equal to n cubed, isn't it? For n larger than 1? I apologize, I started that. I was up here hacking away and now I've passed it on. Well, doesn't that mean that 1 over n cubed plus 2 would be less than or equal to 1 over n cubed? For n greater than or equal to 1? Well, there's our larger term. Isn't that a p-series? What's p? So does this converge? So our series converges by comparison to 1 over n cubed. Let's look at the series of 1 over n factorial. We must decide, do we think this converges or not? Because if you do the limit, that nth term goes to 0, so divergence test fails. I suppose you could try integral test. But what's the antiderivative of 1 over x factorial? I have no idea. It's not p-series, it's not geometric. It's not harmonic. It would be arithmetic. Did I introduce arithmetic? It will not be arithmetic. It's looking like arithmetic series has to be integers. sum of integers would be arithmetic. Well, look at this and I go, n factorial. Definitely larger than n cubed after a certain point in n. Well, if 1 over n cubed converges, then I would think 1 over n factorial converges. So I'm going to go out on a limb and I'm going to say this series converges. I'm going to try and prove it with comparison. The 1 over n factorial. Right? 1 over n times n minus 1 times n minus 2 times n minus 3, and so on and so forth, times 3 times 2 times 1. Well, this would be less than or equal to one over 2 times 2 times 2 times 2 times 2, so on and so forth, times 2 times 2 times 1. As long as n is greater than or equal to 2. Times 1 isn't going to change anything, right? So how many 2's do we have? I'm sorry, this is actually true for n greater than or equal to 1. How many terms were over here? And if you take n factorial, how many terms do you have? N of them. Well, that 1 doesn't matter. So over here, we'd have to have n terms, right? So how many 2s are there? N minus 1. One over n factorial is less than or equal to 1 over 2 to the n minus 1. Right, for n greater than or equal to 1. Take a look at this series. Series n equals 1 to infinity of 1 over 2 to the n minus 1 is the same as the sum n equals 0 to infinity of 1 over 2 to the n. Right? All we did was shift the index. What kind of series is that? Does it converge or diverge? What? Why? What's R? R is a half, right? Absolute value of a half less than 1 converges. Found a smaller term whose series converges. I'm sorry, a larger term whose series converges. Yeah, I'm going to do that 1 to infinity of 1 over 2 to the n minus 1. So the series 1 over n factorial converges by comparison to the series 1 over 2 to the n minus 1. Let's look at 2 plus 3 over 2, 2 cubed plus 4 over 2, 3 cubed plus 5 over 4 cubed, plus so on and so forth. Write this in sigma notation.
past one, n plus one over n to the.
There are two ways to go about this. I think I'm actually going to choose the easier path that I just saw. N plus 1 over n cubed. Can't we write that as 1 over n squared plus 1 over n cubed? Remember, summation is linear. So we can split that into two series. So we have the sum of two series. That first series, does it converge or diverge, and why? What's P? First one. Right. Right. So why does that mean convergence? It's trying to use divergence test. And divergence test is the only one where you take the limit of the nth term. You're right, it does converge. Right. First one is P series of P equal to 2, that's larger than 1, so it converges. Second one, P is equal to 3, which is larger than 1, that converges. Both series are convergent. So we wrote our series as the sum of two convergent series. So the series has to converge. All right, take the sum of convergent series, it has to converge. Take the difference of convergent series, it has to converge. The product of convergent series has to converge. The quotient of convergent series would converge unless the series in the denominator converges to 0. This can all easily be proven because series are just the limit of the partial sums. And then we just use the limit laws from Calc 1. By the way, if you take a constant multiple and multiply it by a convergent series, it converges. That one I didn't even need a test for. What about 1 over n to the n? Do we think it converges or diverges? How would you go about showing it converges? You don't need to go into detail, just like give me an outline, like what test would you use?
Like, show it as a geometric series. And use like 1 over R being, or like R being 1 over N.
That's not geometric. R has to be constant to be geometric. You're on the right track with thinking about it geometrically. So it kind of behaves like a geometric. Right? When I compare it to a geometric series. Specifically, one that we know converges. One over n to the n would be less than or equal to 1 over 2 to the n. As long as n is greater than or equal to 2. This might work.
So is 2 just like your test value?
That's when this inequality is true. It wouldn't be true for n equals 1. Because you'd have 1 less than or equal to a half, which is nonsense. But for every value 2 and larger, that is true. So we look at this. We have to shift the index to make it geometric. I notice it has to start at 2 because we said this comparison is true for n greater than or equal to 2. So I'm shifting the index down by 2, so I have to replace n with n plus 2 in the actual summation itself.
It'd be simpler to just use 1 over n squared, right? Then not have to change indices.
You would n squared would be larger, wouldn't it? The 1 to the first over 1 squared, they're the same, so less than or equal to is fine. 2 squared, obviously they're the same. 3 cubed versus 3 squared, yeah. No, that one would work. You could do that. And then you won't have to worry about shifting the index. Because that'd be P series, which converges. I'm going to stick with this. Just to show the cases where you can't do that. Right? You're forced to go at some value beyond what you're starting at, how you would still work around it. And so this would be 0 to infinity of 1 over 2 to the n times 2 squared, right? So that'd be quarter times 1 over 2 to the n, which is geometric. Go. Is a divergent geometric series, right? C is a quarter, R is a half. Two to the n plus 2. Isn't that 2 to the n times 2 squared? Right, properties of exponents. Multiply, same base, you just keep the base and add the exponents.
Oh.
I'm just going in reverse. So the series n equals 2 to infinity of 1 over n to the n converges by comparison to the series n equals 2 to infinity of 1 over 2 to the n. But that was not our original series. Our original series was n equals 1 to infinity. But can't we write this as 1 plus?
Can you just say that you can remove any finite number of terms?
This is proving it. Well, verifying it for this. Right. In the actual test itself doesn't state that.
Well, yeah, not
So-
that test, but we still know that.
Right. So to use the test, so in math, sadly, when you want to use things like this, you have to have it match the exact form. Right. So I can't just use the test like this and say, oh, I'm done, because this was for 2, not 1. That's not what the test says. But ultimately, you're right, because you can just take out a finite number of terms from the beginning and it doesn't affect convergence. If you let n equal 1, you just get 1 here, right? So what we're doing is we're pulling out the n equals 1 term and add it to what's left. And we've just shown that this converges. So our series is 1 plus some convergent term, which converges. So you're done. Ultimately, it doesn't matter. If you take out a finite number of terms from the start of any series, it does not affect convergence or divergence. Likewise, if you add a finite number of terms to a convergent or divergent series, it doesn't affect it. It will still converge or diverge. Adding or subtracting finite terms doesn't affect convergence. It'll affect what it converges to, right? But it doesn't affect the fact that it converges. Which again, think about it, makes sense, right? Add a finite number of terms to something that converges, and let's say those finite number of terms add up to 100 googolplex. Some constant plus something that converges. Still converges. Sum n equals 1 to infinity, n squared plus 1 over n cubed plus 1. Divergence test fails. It is not geometric. It is not a p-series. You could do integral test. P series is of the form 1 over n to the p. Right, but this series itself is not a P series. Right, so that takes away that nice shortcut. You could compare it. You'd have to find a P series and you have to show that it is indeed larger than this. Which for this one is going to be tough because of the way the numerator is set up. Could try integral test. Integral test will work. Problem is, that's going to require partial fraction decomposition. Combine that with the fact that it's an improper integral, and that's a hard pass on for me. Direct comparison test is going to be a little tricky. But when I introduced the direct comparison test, I said it was one of the comparison tests. There is a second comparison test. The limit comparison. Consider this limit. Limit as n approaches infinity of a sub n over b sub n. Both an and bn will be greater than 0. Again, this test only works for positive series. There are 3 outcomes. Not equal here. If L is greater than 0, I need to specify and finite. Then AN converges if and only if BN converges. This is typically the outcome we aim for. We try to find a comparison series that gives us a limit greater than 0 but finite. Because then we know that the series behave identically. Both will converge or both will diverge. That's the easiest outcome. If L is 0, then if Bn converges, so does A sub n. All right, that falls into the first outcome of the direct comparison. The only way that limit is 0 is if Bn is larger. If L is infinite, then if AN converges, then Bn converges. Right. Again, this falls into the first case of direct comparison, except now your AN is your larger, right? Because the only way that limit is infinite is if AN is larger. Lovely. What the hell? Go away. This is the last test that's introduced today, I think. Let me double check. Yep, it is. All right, so 3 tests and a new series. That's 4 things that should be added to your series sheet. So consider the limit n squared plus 1 over n cubed plus 1 divided by 1 over n. That would just give us the limit of n cubed plus n over n cubed plus 1, right? What's the limit? 1. My comparison series was 1 over n. What does that series do? Well, the terms decrease, I agree with that. The series itself doesn't. Like, you keep adding terms to it. So it's going to keep getting larger. Does this series converge or diverge? It diverges. Why? This is the harmonic series. So our series diverges by limit comparison. Okay, 1 is finite and larger than 0. So glad you asked, because I was going to ask that question. Look at n squared plus 1 over n cubed plus 1. For very large n, how does that behave? Behaves as 1 over n, doesn't it? That's how I chose my 1 over n.
Why do you divide by that?
Limit comparison. An over bn, that limit. All right, so a sub n is the top. That's the n squared plus 1 over n cubed plus 1. B sub n is the denominator. By b sub n, I chose to be 1 over n. Right, and then limit comparison says as long as that limit is finite and greater than 0, the series do the same thing. So if my comparison series diverges, so does my original series. If my comparison series converges, so does my original series. Could have also easily just done it the other way. Put 1 over n in the numerator and the other one in the denominator. It's the same thing. Your comparison is still the 1 over n. Summation n equals 2 to infinity of 1 over n times log of n. Do we think convergence or divergence? How would you go about showing it converges? Okay, so let's take the integral. Well, first we have to make sure that the conditions are satisfied. Clearly continuous. Right, there's only 2 points of discontinuity. There's 0 and 1, neither of which are in our interval. Clearly positive. X will always be positive. Log of X is positive on that interval. It's also fairly obvious that it's decreasing. Right, X times log of X itself is increasing. Both terms increase as you move to the right. So 1 over that has to decrease. Yeah, if you don't see it, take the derivative, which is a fun derivative to take. So we want to take that integral. It's not 1. All right, the only thing that makes this integral improper is the fact that it's an infinite interval, right? There's no discontinuity. What is that antiderivative? What is it? Notice you can drop the absolute values, right? Because log X is guaranteed to be positive, so you don't need them. This will be the limit as b approaches infinity, log of the log of b minus log of the log of 2. What's that limit? It's infinite. Series diverges. By integral test. We jumped right to integral test, but this problem had a purpose. If you look at it and you think divergent immediately, and you try comparison test, that doesn't tell you anything. This 1 over n diverges. That won't tell you anything either. 1 over log n happens to diverge. You'd have to try and find a smaller series that diverges. That is not so easy to do. This is a case where you have to use integral test.
Can you use
Would you? Would
limit comparison?
would limit comparison work?
I think so.
What'd you compare it to?
1/n.
That would leave you with limit of n squared times log of n, which is infinite, which says a sub n converges if if a sub n converges, then b sub n converges.
Would it not leave you with 1/log of n?
Oh, I'm sorry, it's 1 over n log n. That's right, 1 over log n, which is 0. Which says if b sub n converges, then a sub n converges. B sub n is 1 over n, that does not converge.
But doesn't it also say if a sub n converges, b sub
No, that's if L is infinite.
I'm pretty sure you wrote double arrow.
That's if L is greater than 0 but finite. Right, that's why that's always our goal, to try and get that case, because that one's the nice one. 0 and infinity suck. Yeah, I don't know if limit comparison would work. I'm sure it does. You just have to find the series to compare it to. But integral test, actually, believe it or not, is easier here. So notice in all of these problems, you're not told what test to use. That is what makes this difficult. You have to decide what test to use. And then you have to be able to interpret the test properly. Do enough of these problems, and you will start to see patterns. You'll be able to look at a series and immediately know what test to use. But that only comes with doing enough problems. I would say do enough problems to be equivalent to doing math for 20 years, but that would take you a while. Once we finish, so once we learn all the tests, there is a general order to try the tests. Right? 9 times out of 10, one of the first 2 are going to give you an answer, which is nice. Of course, you know, for a test, I'm probably going to pick the 1 out of 10 that doesn't. In which case, then you'll have to use one of the other methods. Questions on anything we've done today?
Still a little confused where you got the 1 over n. I agree. I'd find 1 over n.
Let n be very large. How does n squared plus 1 over n cubed plus 1 behave? Well, not necessarily approach, but how's it behaving? Right, so think of it this way. Let n be really large. Does that plus 1 matter? So n squared plus 1 is kind of just like n squared, isn't it? That n cubed plus 1, kind of like that n cubed, isn't it? Well, it's n squared over n cubed. So for very large n, it behaves as 1 over n. Yes. Because n's approaching infinity. Right? So n is very large. That's why you're allowed to do that. Right? Clearly not true for small n. But for very large n, it behaves as 1 over n. Any other questions?
So that one, could you also have done? You first have to show that when you take away both of the ones, you make it smaller. And
Yes, if you can show that, that would
I
work.
think you could. I thought about it a bit. It seems kind of annoying, but
Right, it's gonna be annoying to do. Right, so if you can actually show that, then yes, that'd be fine. I'm gonna tell you though, that's gonna take a lot longer in a test to show than just using limit comparison. But it is valid. Anything else? Well then. Why aren't you shutting off? There we go.
Your first proper assessment on series convergence.
So that could be either really good or really bad.
It's bad.
You too.